By David Tsang, and he will tell you what it's about.
Hi, I'm Dave. I am a postdoc at McGill. I'm going to be a postdoc in Maryland in a couple months. But this is the end of the long string of people from Cornell, that, past and present at Cornell. So, all right. Okay, so I'm going to tell you about some work I've been doing at McGill about what I call the Eccentricity Valley, and more specifically, it's about eccentricity excitation of giant planets from the disk. From the disk? What? Disks always damn eccentricity. We'll get to that. Thanks for asking. Okay, so this is work done in two papers by myself and by Neil Turner and Andrew Cumming. Neil's at JPL, and Andrew is my supervisor at McGill. Okay, so there's a lot of work done trying to explain the eccentricity distribution of giant exoplanets. In particular, here are three different big simulations, well, nice simulations, about scattering around giant exoplanets, trying to reproduce that eccentricity distribution. And they have a really hard time, particularly for planets that are sort of all jammed up close in towards the star. It's really difficult to sort of reproduce the eccentricity distribution everywhere. So, as earlier, do disks dampen eccentricity? Okay. Well, you have to ask, okay, how do disks affect eccentricity? Eccentricity is controlled by basically changing the energy and angular momentum ratio. Okay. So, if you change the energy and angular momentum ratio, the energy and the angular momentum in the right way, the eccentricity won't change. But if you pump one faster than you should be compared to the other, then eccentricity will vary. And it turns out that the different resonances in the disk, the first order resonances, the important resonances here are the outer first order Lindblad resonances, which tend to pump the eccentricity, and the inner or co-orbital Lindblad resonances, which tend to really damp out eccentricity. And for a planet that's embedded in the disk without having cleared a gap, a type 1 planet, a type 1 migrating planet, these guys win by a factor of 3. So planets of type 1 migration always will dampen eccentricity from the disk. Okay. However, well, there's some arrows. Okay. So, however, if a gap is cleared, you don't have any gas in here to interact at that co-orbital Lindblad resonances. So these guys are still pumping, but it turns out that because you have this sharp transition here, the corotation torques get pumped up. And those corotation torques will damp out the eccentricity. Okay? But it's a much more delicate balance. It turns out that if you sort of use an isothermal response, then you'll find that for reasonable gap models, you get about only a 5% damping compared to the damping exceeds excitation by only 5%. Okay. Goldreich and Sarri proposed that, and Gornobi proposed that maybe eccentricity growth will occur if the corotation resonance is saturated, because corotation is known to, it doesn't really transport angular momentum, it just sort of dumps it in one spot. So you can easily imagine saturating. However, subsequent locally isothermal simulations showed you didn't get eccentricity growth from these things from a disk unless the gap is so wide that you're completely missing all the corotation resonances. And you only get the pumping from the external Lindblad resonances. Okay. So that requires a huge planet. So for something like a Saturn or a Jupiter mass planet, it's not going to work. However, the key was that we were talking about an isothermal response. Okay. So I did some work. This is a simplified formula. I'm not going to show the full formula because showing hypergeometric functions in a 10-minute talk is a little bit like opening the Ark of the Covenant. But suffice to say that this is the limit of a very complicated function. However, it's basically the same factor that comes in to the Rossby-White visibility. Okay? So it's what sets the torque is really the derivative of this quantity called the vortensity, or the effective vortensity here, where the effective vortensity has an extra factor of an entropy to the 1 over gamma n. Okay? What that means is that because these gap edges go down, towards the middle, so the density drops. That's what makes the torques damp so strongly. Okay? Because the density and the entropy are both in the bottom, if they have opposite slopes, then having opposite slopes will cancel out some of that torque, causing the eccentricity damping to be reduced. Okay? And it turns out you only need to reduce it by 5%. You only need to have 95% of the rotation torque in order to allow eccentricity pumping. So how do you get a rising entropy gradient at the edge of a gap? Well, you just heat it up. And you can heat it up by having the stars shine light on the gap. It hits the gap edge, which radiates back and forth and heats up that gap edge. And this is a radiative transfer model by Neil Turner, which I just sort of appropriated from his 2012 paper, which just looked at a gap sitting where Jupiter sits, heated by a sun-like star, an early sun-like star. And lots of things go on here, but the important thing is you want to look at the green line, which is sort of the important logarithmic temperature density ratio, slope ratios. And you see that you want to compare it to this chi factor, which is the gain from the adiabatic torque versus the isothermal torque. And you see it's only 0.75, which means that the corotation torque gets reduced by a factor of 0.7 of three quarters. Okay, you only need to get to 0.95 in order for eccentricity pumping to occur. Moral of the story is that eccentricity pumping can occur if you can heat this gap. Okay? I'm glossing over something here that's a little bit important in that there's timescales that are important here. The important timescale is the thermal diffusion time versus the libration time of the gas. So this isn't going to work really, really far out, where it takes so long for orbits to occur that the gas has enough time to cool down. But very close to the star, the gas doesn't have enough time to cool down compared to the libration time. So this really works. We're close to the star, but not out beyond Jupiter's head. Okay, so gap. So with that caveat, gap heating can cause eccentricity excitation. Okay, giant planets can have their eccentricity pumped by the disk, and most people assume that they don't. Thermodynamics is important, it turns out. That's shocking, I know. Okay, so we went looking for other signatures of this. Becky Dawson and Ruth Murray Clay in 2013 pointed out that there was this thing they called the lack of eccentric valley planets. And I misread that and thought eccentric valley was a term. And so I called it the Eccentricity Valley, accidentally. But anyways, that's the coinage now. So what we're talking about here is that low metallicity, there seems to be a lack of low metallicity eccentric giant planets. Okay, so in this little box that's identified by Becky and Ruth, there are a lack of giant eccentric planets. You might expect that, you might say, oh, well, there's just a lack of planets in general there. Okay? But if I plot the planets with eccentricity less than 0.2, there's plenty of them in there. In fact, if you squint at this, and people that like statistics have looked at this and said, oh, maybe that's actually high. I don't believe them, but they claim it's high. There's more circular planets in here than there are given the rest of the sampling. Okay, so if we look at this, we say, okay, well, how can my eccentricity excitation mechanism explain this? Okay, I didn't really get to that part yet. I think what's going on here, and this is a little bit of speculation, put my speculation hat on, is disk self-shadowing. Okay? If you have an optically thin gas interior to the dust sublimation radius, then light from the star is going to directly hit that dust sublimation radius and cause a big puffy rim. Okay? And this is known to occur. People observe T Tauri systems with near-infrared excesses at 1500 Kelvin, which is right at that dust sublimation radius. Okay? And that puffy rim can shadow a portion of the disk. And remember, we need, if a gap exists, if the planet and the gap exists in this shadow region, it won't get heated. And you'll just go back to the locally isothermal case, the barotropic case, and you'll get eccentricity damping. Whereas if you have an optically thick gas, if the metallicity is high enough such that this gas interior to the dust sublimation radius is optically thick, then you just get a normal flared disk, and you get heating of that gap, and you can pump eccentricity. Okay. So we can look at this, and I can squint my eyes and sort of draw a line here and say, okay, as I turn down the metallicity, I can imagine, I usually use my hands here, I can imagine opening up a gap gradually as that rim grows taller and taller. Okay? And so I think what's going on here is that this is the shadowed region for a lot of these giant planets. And that in there, their eccentricities get damped out by the disk, whereas ones up here, you can start with some eccentricity. Now this is just the initial conditions for scattering, so I don't expect there, it's not explaining everything in that plot. So there are conclusions, questions?
Questions? Yes.
How high can this mechanism pump out this?
That's a good question. So the calculation I did was looking at the linear instability. However, you can't really get a wider eccentricity than the gap width, right? But you're going to run into nonlinear effects well before you get to the full gap width. Like, you know, you're going to have the resonances pile up as you get closer and closer to the edge of that gap. So you're not going to get beyond 0.5 or 0.6. You're probably going to saturate out like, you know, something like 0.3 or 0.4. But it has to be run with a full nonlinear simulation before I can tell you for sure.
Well, I have a question.
Yeah.
Can you comment on the efficiency of this eccentricity pumping as a function of stellar type?
Yes, modulo the effect on the disk. So if you just have the same disk and you have a different stellar type, a larger, hotter star is going to give you more of it. It's going to be able to heat you up a little further away, I guess. So, but the thing about this is that once you reach this linear instability point, it's always going to turn on. So it's an on or off thing. It's not a gradual growth thing.
Gotcha.
Yeah.
Any final questions? All right, well, let's thank our speaker again.